Okay, excellent. Then, good morning, bonjour. Je m'appelle Matthias, but that's the only French that I speak, unfortunately, except for this. Je ne peux pas parler de français. So we will speak in English. I will already share my slides. So topic for today will be filters for electromagnetic compatibility applications. And before we actually start, I have a short survey for you, which is called On a Scale of Artificial Intelligence. How are you doing today? So it would be great if you can all take your cell phone and scan this QR code, and then you should be brought to a website where you can open up the survey. I will also open it up in a second. And by this I also say bonjour and hello to the 2 people watching online. Okay, and there are still 1 or 2 cell phones pointing at me, but now I think there is none anymore. So I will switch over to this website and go to presentation mode. And there are 20 people logged in, and there are still some people coming into the room. Hello, hello, bonjour, come in, welcome. And here should be the questions. And did it work? No. Why not? Probably because because I need to unlock it. So, and I will also unlock the other questions already and go back to presentation mode. And so now hopefully it should work. So I might go back to my slides for a second. So there's the QR code, and the question is, just as an icebreaker question, on a scale of artificial intelligence, the topic that everyone is talking about, how are you doing today? And so we have lots of options here, starting from the mechanical Turk, the number 1, then we have a plain calculator, we have some more or less intelligent coffee machine, we have HAL 9000 from the Space Odyssey, characters from Star Wars and Star Trek, Terminator, Neo from The Matrix, and the paranoid android from the Hitchhiker's Guide to the Galaxy. And now we should have some answers. No, we have 6 answers only, but we have much more people in the room, so I would expect more answers. Okay, now we have 13 answers. This is great, and still some more people coming into the room. Hello, welcome. And there are the results. Unfortunately, I cannot really enlarge them. So there's a winner, I would say, and there are plenty of second places, but the winner with 27% is the number 7, which is Terminator. Okay, thank you for this. So, by the way, if you are on this website, there should be also some Q&A thing where you can write questions in. So, if you have questions in between, feel free to write questions there. If you have questions in between, you can also just raise your arm and ask this question. So here's here's just an hello in this question chat. Have you found this question menu? Yes or no? Yes, okay, thank you. Okay, excellent. So then some words about myself. As I said, my name is Matthias Magdowski. I was born in 1984, like the book or like the movie. You can calculate yourself how old I am. I live in Magdeburg in Germany. I will show you in a second where this is located. I'm married, I have 2 children, and I have a background in electrical engineering. So I also studied electrical engineering. I also did my PhD in this field. What are you all studying? Say a bit louder. Electronic engineering. Okay, electric and electronic engineering. Okay, excellent. Yeah, and so since 10 years or so, I'm also doing stuff like this, teaching as flying faculty. So for a couple of years, I've been to Russia. But this obviously does not work anymore for known reasons, so that's why I'm here, because this is also a nice place. I've been here 2 years before giving a lecture, and I've been here last year giving a lecture, and so I'm happily back again. And there are more students. Hello, come in, welcome, hello. And if you're asking yourself where Magdeburg is in Germany, we are 1.5 hours west of Berlin. So somewhere, let's say, in this triangle between Berlin, Hanover, and Dresden. And this is our faculty building for the Faculty of Electrical Engineering and Information Technology. So some of my laboratories and my office are located in this building, and this is a picture of our city center. So as Angers, we also have a cathedral. As Angers, we also have a river. Our river is called Elbe. And we have a university, and we also have a University of Applied Sciences. I work for the university, which is located in the city center, and our University of Applied Sciences, like the IUT here, is located a bit outside the city. So as here, you take one tram, drive almost to the final destination, and then you are at this University of Applied Sciences quite nicely. Yeah, in the green part outside the city. Hello also to the people watching online. So then some words about Otto von Guericke, who is the name patron of the university where I come from. And he was a mayor of the city of Magdeburg in 1600 something. So a couple of 100 years ago, and he was also an engineer and a scientist, and he also did experiments with electricity. He had a large sulfur ball that could be rotated, and then due to tribor electricity, charges could be separated, and he could create discharges with the sulfur sphere. And he did a very famous, he was also a kind of good science communicator, and he did some interesting experiment. Have you heard about the Magdeburg hemispheres? Yes, some people yes, some people no. So a picture of them is depicted here. So he experimented also with vacuum and with the force of the air pressure. And to demonstrate how strong this force of the air pressure that surrounds us all is, he took 2 large hemispheres, about 60 centimeter diameter, put them together just with a seal, and then he also invented the air pump, and then sucked the air out of it, pumped the air out of it. So there was nothing between the spheres anymore, just vacuum or just very low air pressure. And then due to the pressure of the external air, these hemispheres were pushed together. And to show and to demonstrate how strong this pressure is, he did a very nice experiment. And took 16 horses, so 8 horses on one side, 8 horses on the other side, you can see it here, and they tried to pull the spheres apart. But due to the strong force of the external air pressure, they were not able to do so. And so, very impressive, interesting experiment to show this force, and then the legend says that the small boy child came, opened up the valve, the air would flow back into the hemispheres and they would just fall apart. And sometimes for the anniversary of the university, for example, we repeat this experiment in Magdeburg. So Levi Strauss, if you have jeans trousers, same experiment, different force. Yeah, he also, to show the strength of these trousers, I think he borrowed the idea from us to show this. And there's also an interesting connection with Otto von Guericke and the French language, because originally Otto von Guericke, he was a German guy, was just written like this, Guericke. And then in, I think, 1666, he was by the German king ennobled. So before he was just Otto Guericke, and then he was Otto von Guericke, so he was a noble person. And the language of the kings and the diplomats at this time was French. And if you would pronounce this name in French, how would it sound? Guéric, right? Yeah, and he did not like this. He did not like to be called Guéric, and that's why they did a trick, and they introduced this U in the name. And because of the U, you would not call it Guéric, but Guéric or Guericke. And yeah, so because of this, his name is written like this. Okay, so some organizational matters. If you want to have the slides after this presentation and lecture, you can have them. I will happily share them with Regie and he can spread them, or I don't know, maybe I will upload them to this Moodle system, or you can also just send me an email and I will happily send them. I will also try to do a recording. You never know if it works, maybe, maybe not. So actually I'm doing a live stream, and then the live stream is the recording. And if you have questions in between, as said, feel free to ask these questions. And I'm not sure if there is, oh yeah, there are now plenty of questions already. Hello, my Deutschman. Yes, this is, how are you? I'm fine, ça va bien. This is also something that I've learned. Okay, okay. So then we can start with the topic, and the topic is electromagnetic compatibility. So what is it? What does this mean? And there should be a survey for you. Have you heard of EMC before? And I need to find this. It should be in the question series. And I think we had this question already. So I need to switch to the intro and say, yeah, okay. And so maybe you need to scan this QR code again. If you're on this page, there should be a new question popping up. Have you heard of EMC before? And there should be some answer options, and some cell phones are still pointing at me. That's why I won't switch to the browser yet. But now I will do. And there are 4 answers already. Now we have 8 answers. And a couple of more answers. So maybe I will show the results already. And interestingly, I would expect there to be some labels, but it just says plus and minus. I'm not sure what this means. Okay, but So most people say 0 and most people say minus, minus. Okay, so I would expect you have not heard too much about EMC before. So the brief and general definition, and then we will take a look at some examples later, is what is written here. Yeah? So we are using lots of electronical equipment all the day, cell phones, we have lots of electrical equipment at home, and we expect that this all nicely works together without any interference. And this is what is called electromagnetic compatibility. So devices should be immune to external disturbances and external fields, and at the same time they should not emit unwanted signals into their electromagnetic environment. So there are two aspects in there. And the first one is immunity. They should be immune to external disturbances, and they should not emit, they should not radiate signals into their environment. And we can try to explain this by a simple coupling model. So we have sources of disturbances. This could be, for example, your cell phone, which uses electromagnetic waves to communicate, and the victim could be some control system, for example, in your car. And you don't want to disturb the braking system in your car when you use the cell phone in your car, for example. And some other example is the source could be your Wi-Fi router at home, which also creates electromagnetic waves and could disturb your TV set at home. And now we can take a look at these coupling paths, and the coupling path could be conducted. Coupling could happen via cables, then we would call it galvanic coupling or impedance coupling. Coupling could happen via electric fields, and we would call it capacitive coupling. This coupling could also happen via magnetic fields, and we would call it inductive coupling. And so this here all works at rather low frequencies, or where we have quasi-static fields, and then at higher frequencies the electric field and the magnetic field cannot be split apart. They will always be there at the very same time, and then we would call this electromagnetic fields or wave fields, electromagnetic coupling, radiation coupling. There's a nice talk of a German colleague of mine, Andreas Bachanski, working for Dassault, which is I think also a French company, doing all kinds of stuff, but also developing simulation software. And here's a nice talk about electromagnetic field simulation, where the title is ENH, Instant Best Friends Forever, because the electric field strengths and the magnetic field strengths, you cannot split them apart. They will always be there at the same time. Okay, so now we can have a look at some examples, and I have, for the lecture today, just chosen one example, and this one example is electrical cars. We all know these Teslas, for example. I mean, these persons here are probably not that nice. The car maybe still is, I'm not sure. There are probably also French car manufacturers that do electrical cars. And so if we take a look at the power flow in such an electric car, we have our power grid, the mains grid charger, and this works with AC voltage, right? The voltage in our mains grid is some AC voltage, but the battery inside the car can only store DC current and DC voltage and charges in DC. So we need to have a rectifier in between, which converts AC into DC. And then the motor, the traction engine in the car, once again works with AC, because it's more efficient and better to build AC motors. So we need to have another inverter that converts the DC of the battery back into AC for the motor. And the energy needs to come from somewhere, so you need to charge. This is a quite famous picture on the internet where people made fun of drivers of electrical cars and said, why did not why did this person, if the charging cable is that short, why did the person not simply went in reverse into this parking lot to charge the car so that the cable would be better? If you check for other versions of this picture on the internet, you find out that he was actually towing a trailer, and so because of this it was not possible to go in reverse into this parking lot, and that's why he had to maybe drive over the curb here. Okay, so we can take a look at a bit more into detail in what happens there, and this is how the rectifier looks like. In the charger, let's say. So here is your three-phase AC mains grid voltage, and so the diodes will always only let the positive current go through, and that's why you get a DC voltage on this side, and this is where you would charge the battery with. If you study electronics, you have seen a symbol of a diode before, right? Okay. Yeah, so as discussed, diode works like this. If you have a negative current, it won't get through. If you have a positive voltage across the diode and a positive current, this will get through. And so the inverter on the other side, or let's say inside the car, so here's your battery, here's the motor, works a bit in the same way, so the same bridge configuration, and then you have power electronic switches, MOSFETs, IGBTs, that will switch on and off to certain times, and then you can convert the DC back into AC with some pulse width modulation and so on. And for the other and you need these freewheeling diodes, let's say, for the other parts of the current. Okay, so this is how it looks inside, and the problem from an electromagnetic compatibility point of view are these diodes, or are these switching elements. So this one here and the diodes here, because they switch on and off fast. And so if we take a look at such switching event, the one simple way to describe such a switching pulse is to use this trapezoid shape, or trapezoid, and we can say there's a pulse width and there's a rise time. And if we take a look at the signal, not only in time domain but in frequency domain, if we take a look at the spectrum, then it looks like this, that for low frequencies there's a constant part, then there's a first break frequency or corner frequency that depends on the pulse width, and then it goes down with minus 20 dB per decade. Have you heard of dB before? Have you done calculation in decibels? Okay, excellent. And so then there's a second corner frequency. This depends on the pulse, no, not on the pulse width. This depends on the rise time, and then goes down with minus 40 dB per decade. And so what you can see here, the problem is we get, if we do the switching on and off very fast, so the smaller the rise time and the smaller the pulse width, the higher will be this corner frequencies and this break frequencies. So you get spectral content at high frequencies, and high frequencies means also at short wavelengths, and every cable that you have everywhere will also act as an antenna and will radiate signals and will receive signals. And so switching fast in time domain means you get broadband disturbances in the frequency domain at very high frequencies. And so this is the, I would call it, everlasting conflict between power electronics and electromagnetic compatibility, because power electronic people would like to switch as fast as possible, as I'm trying to explain with this schematic here. So if we take a look at one switching event of this MOSFET or IGBT or of a diode in the rectifier or in the inverter, If the switch is open, we have full voltage across the switch, but no current, right? And if we switch on, we have full voltage, full current through the switch, but we have no voltage anymore. And in between, the voltage needs to decrease and the current needs to increase. And now if we have current and voltage at the same time, what is the product of current and voltage? Power. We get power. So the light blue curve here is the power. And if we integrate power over time, what do you get? We get energy. And so the shaded area here is the energy that is lost in the switch, in the MOSFET, in the IGBT during each switching event. And the power that is lost will be converted into heat. And then you need to cool it, it will lower the efficiency and so on. So from an efficiency point of view, power electronic people would like always to switch as fast as possible. Because that's the only way how you can minimize this energy, because you cannot change the voltage level, you cannot change the current level, you can only try to switch as fast as possible. But going back to the slide before, if we switch very, very fast, we will create high frequency disturbances. Okay, so one way then to get rid of these high frequency disturbances is to use filters. And before we dive into this, I have another survey for you. Do you know other EMC examples? So it should be the very same QR code, but I need to probably activate this question series, which is here the examples, and I need to activate, okay. And so now there should be, let's show this once again for a second. Now there should be another survey for you. Do you know other examples of electromagnetic incompatibilities, some disturbances, some malfunctions, something like this that, for example, happened in your home, that you have observed at the university, or maybe during some work that you did, something like this. And so let's switch back to the page, because there are 4 answers already. Okay, there is some. Interestingly, I did not know that it is possible to post pictures. So we see noise. Unfortunately, maybe I could also try some example. Where's my, So I think I need to show typical disturbances, we can try it out. I have my old cell phone with me. So Bluetooth. Does anyone know at which frequency Bluetooth works? Bluetooth also works at 2.4 gigahertz, so the same frequency as Wi-Fi, the same frequency as your microwave oven at home. That's why Bluetooth headsets often get disturbed if you operate, for example, the microwave oven at home, because it's just the same frequency. The same with headphones. Magnetic field and inductance belongs together. Electromagnetic field can create perturbations on the screen, especially on old TV sets with this cathode ray tube displays. These newer displays, of course, are not that prone to these disturbances anymore. I don't know what this means. Lightning strikes, this is some very good example. Yeah, and so here now my, maybe let me quickly, switch to full screen. So here's my cell phone, and it's my old cell phone. It's a dumb phone. And my children will always say, your phone isn't working, and I said, yo, it's not a touch screen. You have to operate the buttons. And so now it's logged into Orange F network. and I will call my office in Magdeburg. Oh, now I get some short message service first. So let's see if we can create some disturbances with the cell phone. Right, nice cell phone disturbances. And yeah, so I will quit the call again. We can also try it out if it works with the other microphones here in the room. But they are obviously not so prone to this disturbance, but this wireless microphone here in the room definitely is. And so if I quit, then it's gone. If I open up the call again, wait, I get messages at first that I'm logged into a different network. So let's call once again. Yeah, very iconic noise that everyone knows. And so what happens there is that in this old GSM system, always 8 cell phones are using the very same frequency, and that's why they switch the signal on and off. Does anyone know at which frequency such a cell phone operates? No, it's not. It's something lower. So this is working at around 800, 900 megahertz. And of course you cannot hear the frequency, but you hear the shape, how the cell phone switches the signal on and off. This is this that you hear. And it's happening because there are also some non-linearities in the microphone here, and they will demodulate the signal. So you're not hearing the high frequency, you're hearing the shape, how the cell phone switches the signal on and off. Okay, so let me go back to my slides or to your examples here. Okay, and high consumption of all the devices connected. This is something that happens on cables and in the mains grid. If you have many devices on one power outlet and the more you switch on, then of course there will be a decrease in the voltage that can then create other disturbances for other devices. Okay, excellent. So then, as said, we can a bit look into filters, and before we do this, a quick reminder of circuit calculation. So question is, if you want to calculate electrical circuits, what rules do you use or what equations do you use? Just shout something into the room. What equation do you use to relate voltages to each other? Yeah, we have Ohm's law. Ohm's law relates voltage and current at some resistor. But if you have just a circuit and if you just take a look at all the voltages, yeah, so there is Kirchhoff's voltage law, right? That just says if you have a circuit and if you go along a loop in the circuit, then the sum of all the voltages inside this loop should be 0. And we have the same for the current. If you have a node, then the sum of all the currents at this node should be 0, or the sum of all the currents flowing towards the node must be the same as the sum of the currents flowing away from the node. Okay, so then what do you know about current and voltage? You already said there's Ohm's law. So current and voltage at some resistor are proportional to each other. The more current, the more voltage. Yeah, and the resistance is what hinders the flow of current. So what other two circuit elements do we have in electrical circuits? Basic electrical elements. we have capacitors and we have inductors. And so at some inductor we get, or we have Faraday's law and Lenz's law, which says that if there's a change of the magnetic field, and the magnetic field corresponds to the current, if we have a change of the current, then some voltage will be induced. And the voltage will be against the original flow of the current, right? So if we have this changing magnetic flux due to some electric current, then the induced electromagnetic force, the induced voltage will stop, not really stop, but will act as a force against the flow of current. And then, as mentioned, we also have capacitors, and at capacitors it's the same but completely different. It's a dual quantity, so if the charge changes and the charge corresponds to the voltage, then we will have a flow of current. Right, so here we have this time derivatives. If the current changes, some voltage is induced. If the voltage changes, some current will flow. Okay, you have seen about this, right? In some other lectures before. Okay, so next question is, what happens for harmonic signals, for AC signals in the frequency domain? So what happens if we write these equations using complex phasors in frequency domain, and for some resistor, for Ohm's law, more or less nothing happens. It's the very same equation as before, just that we write it with complex phasors. So what happens at the inductor and at the capacitor? Someone an idea? So for the inductor, right, that this AC voltage follows the AC current and is held back by the inductance of the inductor. So the time derivative in time domain will change into a multiplication with j omega in frequency domain. You have seen this before, right? Okay, so this is what we call then impedance. The complex impedance of the inductor is j omega L. The higher the frequency, the higher will be the impedance of the inductor. And so for a capacitor, it's once again the same but different. So voltage, then we have j omega c, and this will give us the current. And once again, remember this guy, right? We have seen him before. So DC cannot pass through, but AC can go through some capacitor, as we have seen in this schematic here before, which is of course not really what happens there. But AC can pass through a capacitor, DC cannot. Okay, and this omega that you see there in this equation, that is the angular frequency, which is 2 times P times F, the usual frequency. And so now we can take a look at some first experiment, and we will start with some resistor. And resistors look like this. Usually they have these colored rings. You should also know if you study electronics. And these colored rings tell you how large this capacitor is. Why should you learn about this? Because maybe you have to solve a captcha like this on a label, take all the 220 ohm resistors, and then you would need to look in this table what this is. Okay, so we can do a first experiment, and I've set up some stuff here for the experiment. So I have a document camera, and now I think I will switch over. Yeah, and thanks to RAM 500 in the chat for the funny presentation. I hope that it is. So now I will switch over to this microphone here, and I need to put the cell phone away from the other microphone. So what I have here is called an analog discovery 2. It's from a company called DIGILENT, which somehow belongs to National Instruments. So it's some device that is like an oscilloscope, and it has analog and digital inputs and outputs. And what I've connected, and so it's connected via USB to the computer. And what I've connected here is a small printed circuit board. As you can maybe read, it says it's some impedance analyzer. So it helps us, or it enables us to measure impedance. And I've connected two small breakout cables, and I have some resistor here. And the label at the resistor, I don't know if it can be seen. It's not too bright here in the room. Says 10K. So it should be a 10. I don't know. I can try to switch a light on here. But now there's some reflection. It should be a 10 kilo ohm resistor. So let's connect this resistor. And maybe before we measure with the impedance analyzer, of course, I also have a plain multimeter here from Fluke. So we can check before what happens here, and then you can see, okay, it's not exactly 10 kilo ohm, but 9.97. Okay, excellent. So then let's connect the resistor to this impedance analyzer. And it's really not very bright here in the room. Okay, so it's connected. And now I need to have the corresponding software, which I've already opened up here, which is called Waveforms. And then we can go to this impedance mode. And so now set the device to measure here the magnitude and the phase of this impedance, and I will use a frequency range from 100 Hertz, which is here, up to 100 kilohertz, which is here. And so we can measure with 100 frequency points per decade using this adapter, and then I can press single. So what would you expect if we measure the frequency dependent impedance of a resistor? What curve should we get?
The resistance not change.
It should not change with frequency, so it should be a constant curve. So let's check. And it's measuring, and so you can see the constant line here. The scaling a little bit fails because the 10 kilo ohm is exactly on top of the curve, but here's the constant line for the resistor. I'm not sure if it can, there I can change the scale. So as you can see, we get a constant line and we get zero phase, which perfectly makes sense. Okay, so let's go back to the slides. Next thing that we can measure is a capacitor. No, a capacitor, not a capacitor. But yeah, remember this. This is also important for your electronics studies. Every device is a smoke device if you operate it wrong enough. So let's switch back over to my document camera. And I also have a capacitor here. It's this red thing. And this capacitor is from this box here. which is, you can see, is some Design Your EMC filter kit from a German company called Electromagnetic. And if you open up this box, then there is a list of all the components. So the capacitor that I'm using now is this one here. It should be a 0.15 microfarad capacitor. And the components are all in here. So it's just one capacitor from here with this J03 labeling. And yeah, so it's this capacitor here. I will remove it from the small breadboard and connect it to my impedance analyzer here. Putting away the resistor. So one cable is connected and the other cable needs to be connected on the other side. Okay, so there the capacitor is connected. And I can go back to the measurement program here and hit single. So what would you expect now if I measure the impedance of the capacitor? It should not be constant anymore, but the impedance of a capacitor is 1 over j omega c, so 1 over omega. So for small frequencies, it should be high, and the higher we go in frequency, it should go down. And this is what we see here. So we see that the impedance decreases with frequency, and that we get a phase shift of minus 90 degrees, which perfectly makes sense because this is the 1 over j, which is minus j, which is minus 90 degrees. Okay, so last element that we can try is some inductor, right? This guy again, but for the inductor, the DC can get through and AC will be blocked. So we can also try to measure this. And for this, at first I need to have my document camera once again. And as an inductor from the same box here, I will use something that really looks like an inductor. As you can see, one coil like this. And this is a special type of inductor, especially used for filters. It's called a common mode choke. We probably won't have enough time today in this basic lecture to really explain what this does, but it's like two inductors on one common core. This is what happens here in this element. And so I can try to connect this to my impedance analyzer here. And then you can already think about what should happen if we measure the frequency dependent impedance of some inductor. So if I click start, if I click single, what would you expect? Now, a person is making the right sign. We should see a curve that goes up because because we should the impedance is j omega L, it's increasing with frequency, and we should see a 90-degree phase shift. And we see a 90-degree phase shift, at least for the higher frequencies here. The phase is a bit going down. If I decrease the frequency range a bit and go down to 10 Hertz and try to measure again, then of course for the low frequencies it takes a bit more time to do the measurement, but then we can see that at small frequencies the impedance is not really increasing already. It's more or less staying constant. And the phase is rather small. It's at about 10 degrees or so. And then if we go to higher frequencies, as we have seen before, the impedance increases. So why do we get this constant behavior at low frequencies? Why does the j omega L does not work at lower frequencies? You have some idea? Yeah, so now we can see, now we have the j omega L behavior, now its impedance increases, but for small frequencies it stays rather constant. So why it's like this? It's because what is this coil made of? It's made out of a wire, and the wire also has some resistance. It's made out of copper. So what we see for the low frequencies, it's just the resistance of the wire. Okay, so after repeating the basic behavior of the basic circuit elements, we can take a look at filters and can discuss at first what means filtering. And filtering for the electrical signals is like filtering for other stuff. We want to separate something good from something bad. My usual example is a coffee filter, right? You want to have the good taste of the coffee, but you don't want to have the coffee powder in your mouth. So you need to have a filter that separates the tasty water, the coffee, from the coffee powder. Interestingly, on my way here, traveling with German trains and French trains, there are interesting coffee cups that are sold on German trains. So it looks a bit like a usual cup of coffee and you get some milk with it. But if you open it up, you find out that they just put coffee powder into the cup and pour boiling water, hot water over it, and then this lid or the cap of the cup, this contains the filter. So if you drink, you should not drink the coffee like this, because then you get the coffee powder in your mouth. You always need to, it's a filtering lid. Have you seen something like this before? No. I think it's something special on German trains. Okay, so the same stuff is what we would like to do for electrical signals. So let good signals get through and attenuate unwanted signals. And so here, this is a new QR code, and I think I need to open up the corresponding software, which should be, why is this? I'm sorry, I need to open up the program once again for this. I think now I remember why it's not here anymore, because I had to restart my computer in advance. So let me find this quick. There is the corresponding program, there's the corresponding version. And I need to click OK, and I need to reshare my screen. Okay, and so now you can scan this QR code. Oh, and someone said, Ulrich der Zocker wrote in the chat, I got the same cup on Austrian Airlines. Okay, I've never heard of this before. Okay, so this obviously works now. So the idea is, I will at first hide all the other drawings. So you have some space here. You should be able, using your finger, or if you have a stylus on your cell phone, to draw something. So please sketch a schematic of a first order low pass filter. So how should a first order low pass filter look like? That you build from, for example, one resistor and one capacitor, or one resistor and one inductor. And think about inductors let DC pass and block AC, and a capacitor will block DC and will let AC pass. And usually for EMC applications, we, in most cases, need to have low-pass filters because the low frequency signals are the useful signals that we need to operate, for example, for the electric vehicle, for the motor, but the AC signals, the disturbances, that should go away. Okay, so let's see if we have some solutions already. Oh, and there's someone has drawn something with some power, with some operational amplifier, and I think this is really a low-pass filter due to this capacitor. But these operational amplifiers are not really useful for EMC applications because the filter should be a pure passive filter. We want to have high current, high voltage in this filter. So I think this is more, yeah, and it's also important to mention him for sure. This more looks like a high-pass filter for me because DC would be blocked by the series capacitor. So remember this for the AC filter. Okay, here we have another operational amplifier circuit. I think this should also be more like an AC, like a high-pass filter. This looks good, right? So here the resistor will let signal through, and then the high frequencies will be dissipated, will be attenuated by the capacitor going to ground. And this here also looks good and looks perfect for this application. I think this also works. This is a nice guy. This also works. This also works. This is not fully drawn yet. Okay. And we have some more example here. Excellent. So maybe I should save this somewhere on my computer as low pass. Okay. Thank you. So then I will, for a quick moment, show all the schematics, which always looks nice. And then I need to find a button to delete all stuff. So I'm sorry, I need to delete it and show nothing. So maybe, yeah, so here are schematics that would work as a low-pass filter. So here the capacitor, the inductor will let signals through, and the resistor is just then the shunt element. And here the resistor will let everything through, and the DC, the capacitor will divert the AC signal back to ground. Okay, so maybe another thing that we can do is how does a low-pass filter behave? So please sketch, you're all on this page because the QR code is missing here. How does the amplitude response of such a filter look like? So please draw. We have here on this axis the angular frequency, and we have here the ratio between the output voltage and the input voltage, and just the magnitude of this, and how should this look like if we have a low-pass filter? How should the amplitude response or the transfer function of such a filter look like? And there are some ideas already. So this looks very good. This is also looking fine. This is also looking fine, also including the minus 20 dB per decade. Okay, excellent. So many right and many good solutions. I will once again, and this is also looking nice. So let me try to save this also. And so I will save it as low pass too. Okay, very good. But we can see very many good solutions. This one here would be not that good because here high frequency signals would be even amplified. Okay, excellent. Thank you for this. So, I will skip through the other examples to save a bit of time. So if we have a high pass filter, we can build it the same way, just that the position of the inductor and the capacitor are interchanged, right? And then a high pass filter transfer function would look like this. Low frequencies get attenuated, high frequencies get through. And then if we would have a filter with such a transfer function, so some resistor at the output and then the total voltage across some inductor and capacitor, we would get a circuit like this. And now imagine what would be the purpose of such a filter. Draw again? Yeah, exactly. So the low frequencies can get through the inductor but will be attenuated by the capacitor. And high frequencies will be blocked by the inductor and can get through the capacitor. So high and low frequencies both will be blocked, but there's some frequency in between that can pass. So this will be a band pass filter. It will look like this. And depending on the quality factor and the value of this resistance, it will be more peaked or less peaked, but this would be a band pass filter. Okay, so to prepare some stuff for the exercises that we will have in smaller groups, I think tomorrow and the day after tomorrow. Now, what I would like to do is I would like to measure the input and output impedance of a real filter. So what I've got here and switch back to the other microphone. So what I've got here is also from Electromagnetic, from this German company. This is a real commercial power line filter that you could buy if you want to filter disturbances of some appliances. And it's for 250 volts AC, so it's for mains grid voltage, and it can handle up to 1.5 ampere of current. And yeah, so unfortunately you cannot look what's inside. And some idea is we would like to find out what's inside. We can have a lucky guess what's inside. And the lucky guess would be there is some capacitor and there's some inductor. And so now the idea is to find this out. We measure the input and output resistance or impedance. So at first I will connect my impedance analyzer to the input. So now we have the input. And I can go back to the measurement program here. I will go back to 100 Hertz of starting frequency and click on signal to do the measurement. And now we can see, okay, we get some impedance that decreases with frequency. So what does it mean? What do we see? What is the element more or less that we are measuring now in our filter? It's some capacitor. So at the input, there seems to be some capacitor. So now I need to have from another box a small short circuiting cable. So what I will do now is I will short circuit the output. So now you can see I have a cable at the output that connects the output terminals with each other. And I will try to save this first. And then hit the signal again. And so now the output is short-circuited of the filter. And as you can see, we are measuring a different impedance. And it's staying constant. It's staying constant and it's going up with frequency, reaching some maximum and then going down again. So if we look at this behavior here, what is the circuit element that we are more or less measuring now? It's some inductor, some inductance. And this is the resistive part, and this is the inductance. And then we have this kind of resonance also that we have seen for the bandpass filter before. Okay, So maybe do a quick screenshot of this. So now I will do the same, but just from the other direction. So disconnect these cables once again here, turn the filter around and measure the impedance from, let's say, from the back side, from the back door. So filter is connected. And I'm hitting this measure button once again. So we see impedance decreases frequency. What circuit element do we once again see now from within the filter? The capacitor. And we also see this kind of resonance, and then that it's going up again. And let me take a screenshot and go back to the camera. And so I will now connect this short circuit cable at the input, which is now nicely connected. And just measure the impedance again. And now, once again, we can see, okay, impedance is staying constant, it's very small. There's also some noise in this measurement because the values are so small, but then impedance is increasing and we just see this ohmic inductive behavior. Once again, some resistor and some inductor. Okay. So this was the input and output impedance of this real filter. And the last thing that I would like to measure with my equipment here is now really also the transfer function of this filter. So what is the ratio between the input and output voltage? And yeah, for this, I need to go back to my document camera. And I think I need to close also the software here, because I need to have a bit of a different setup and I don't want to save. Okay. So I need to disconnect this and also disconnect the filter here. And so I've brought another one of these Analog Discovery 2, and there's, as you can see, another breakout board here. And this breakout board is, as I've said before, like an oscilloscope. So there are two channels here. This is channel 1 of the oscilloscope. This is channel 2 of the oscilloscope. So I can measure two channels. And these are two waveform generators, like a signal generator. So with this side here, I can generate a signal. And so here's my filter, and now I need to have this larger breadboard here because I need to have some input and output resistors. And this is now a bit of a complicated setup. So at first I need to have a cable. This will be my, and I've decided not to set it up at the beginning because then it's a very complicated setup and no one really understands what I'm doing here. So I have a first cable. This cable will connect to the waveform generator here. This will be my source. And the source will be connected to the input of the filter, and usually the source also has some impedance and some resistance, and the impedance here unfortunately cannot be too small because this waveform generator is not that powerful. So I will use a 50 ohm resistance. I did not found a 50 ohm resistor, but this resistor should be 47 ohm or so. So here are the measurement cables of my multimeter. Here's this resistor. And as you can see, it's something like 47 ohms. Okay, so I will connect this to my breadboard and connect the source to this resistor. And now I need to have a short cable going from this resistor to the input of my filter. Okay, so the input is already connected. Now I do the same at the output. So I have another one of these resistors, and I will, or maybe do it like this. I will also use two cables to connect them to the output of this filter. Okay, so what we have now is, here's my pen for showing this a little bit. We have a 50 ohm resistor or 47 ohm resistor at the beginning of the filter and at the output of the filter. And so filter is set up. Now we just need to have two more cables to really do the measurement. And for this, I use these typical oscilloscope cables, probe cables that you might have seen before. So I will use the yellow cable, connect the yellow cable to port number 1, and I will use the red cable to connect it, and it's fairly tight, to port 2. And what is quite important, that both cables should be set to a divider of 1. And so now with the yellow cable I can measure the input voltage. And with the red cable I can measure the output voltage. Okay, so that's my measurement setup, and thanks for the subscription. So let's go back to the software that I need to open up again, and it's called Waveforms. There it is. And my computer is a bit slow, and it's a bit hot, but and I think it's just telling me in the background that there's no device yet connected. Because, as usual, old engineering rule, devices work better if you turn them on, or if you properly connect the cable, so the USB cable is missing. Okay, so let's retry, and there it is, and now we can go to network and see now that we can try to do the same frequency range starting from 100 Hertz up to 100 kilohertz. And I think I can just say single and go. Okay, and then what we would expect is that we see a curve that is okay, at first staying constant because low frequencies should get through, and then we get some attenuation at the output. The 100 kilohertz is obviously not high enough to see some real effect here. I wonder if everything is connected correctly, but I think so. So let's go for a bit higher frequency. Let's go to 1 megahertz and measure again. Okay, and we can see that something interesting happens. So the filter is measuring, but then we get some kind of resonance. So let's repeat this measurement. So low frequencies get through, and yeah, after 10 kilohertz or so, some attenuation kicks in. Then we get this kind of resonance, and then the attenuation is at another much smaller level. Okay. So I might repeat the measurement with a different position of the probe cable. So now I have connected it to here. Let's see what it does and what happens now. But I think, no, this is not useful. Okay, so we will leave it as this. I will just connect the other cable here. Okay, so let's try a last measurement. But I think it won't get any better than this. So this is then how this filter here, this real filter, behaves if we are measuring this transfer function. And we can see, okay, it's staying constant as what we have seen before, then it's going down, we get this resonance. Okay, that's it. Okay, and so maybe I will extend it once again to 10 megahertz and do a last screenshot of this behavior. And so then what I can tell you that what we will do in the exercise is we will meet in smaller groups. And have you experience with LT Spice with the circuit simulator? Yes, okay. So the idea is that you are then trying to model, trying to replicate the behavior of this filter in LT Spice. And one important effect that we will think about is what is happening here. What is happening at this point, because usually you would expect your filter that attenuation stays constant and then transfer function is going down. And it should go down, but why is it going up again? And why do we see this resonance here? Yeah, what is causing this kind of good but then bad behavior of the filter? This is the question that you are trying to solve. Okay, so let's go back to the slides and let's finish with some quiz. And for the quiz, let me at first show the prizes that you can win. So because I have 4 prizes, no, I have 3 prizes. So the first prize is this nice ruler from this company. The second prize is some USB pen drive of VDE, which is German Electrical Engineering Association or Association of Electrical Engineers. And the third prize are some goodies from my home university. A pen and some stickers, always very handy. Yeah, from here, this is like Otto von Guericke, right? The person that we've talked before. Okay, and I think I've opened up the quiz already somewhere in my browser, and let me share my screen once again. And there it is. And then we will go to Live Hosten. And for the quiz, where is it? Ah, here. For the quiz, it's a good old rule that I also need to wear these glasses. So let's click Start in the classic mode. And there is the QR code. And let's go to full screen. And there should be also some music. Ah yeah, there it is. There is the music. And people are logging in. I don't know how many people we have in the room. By the way, this reminds me, this is the point where people are logging in to take the obligatory selfie. Okay, excellent. So everyone logged in? Does anyone need more time? I think, oh, there are still people joining. And I've closed the chat on my cell phone, but okay, there are almost 50 people now logged in, and I think we are ready to go, so I will close this and go to start, and then we have 6 questions according to the topic filters for EMC applications, and the first question will be there in just 1 second, and it's: a low-pass filter allows only signals below the cutoff frequency to pass. How can this frequency be increased? So if we have this filter and we want to have a higher cutoff frequency, what do we need to do? Do we need to have a lower resistance, a higher resistance, a higher capacitance, or can we not change it by changing RNC at all? Because for this purpose we need to have some further inductance. Okay, and the result is a bit, I would not say disappointing, but it looks as if people have just chosen randomly. So we need to have a lower resistance. Lower resistance will make a smaller time constant and a higher cutoff frequency. So let's have a look at the podium. Oh, this is difficult for me to pronounce. Yeah, okay. So we can continue with the second question. What is an analogy of a low-pass filter and its effect in mechanics? So if you have this spring mass system, what corresponds to a low-pass filter effect? Is it the spring? Is it the inertia? Is it friction or is it acceleration? Okay, and it is inertia, because inertia is this creating this counter force, allowing for slow movements but damping faster movements. Okay, and there we have a change of the podium. So Charlie is climbing to the first place, followed by Bob and Ben Laden. So we will continue with the next question. The comment was just here that more than one answer can be correct. So what else could we call this first order low pass filter? Is it also some integrator? Is it some averaging circuit? Is it some PI controller, or is it some smoothing circuit? And let me try to do another selfie in Excellent. So 15 more seconds to answer. Could you also call this, okay, and here in this question, as you can see, nothing could go wrong. All of these answers are correct. Yeah, it works like everything like this. Okay, so another change of the podium. On the podium, Leo is claiming to the first place, pushing Charlie to the second. So we can continue with the next question, which is a true or false question. So a linear passive filter also works the very same way in reverse operation. The blue thing is right, true, and this means false or no. The question is, do we get the very same behavior also in reverse operation? Is it right or wrong? And excellent, most of you have selected the correct answer, which is false. So you get a different behavior if you operate it in the opposite direction. As we have also seen, measuring this input and output impedance. So we come to the second to last question. The performance of the filter depends on the source and the load. Yes, it does depend, right? It's the blue answer, or this is false. It does not depend on the source and load. It's the red answer. And there are 10 more seconds to answer. And I'm curious how the result will be. And okay, most people have selected the right answer. Yes, it depends. Okay, so Charlie still on the first place, followed by Leo and Elliot climbing up to the third place. And we come to the last question, the deciding question in this quiz. What happens to the energy of the filtered components? Will they only be dissipated in the filter and converted into heat? Will energy be also reflected back to the source? Will the energy be amplified, or is it a combination of reflection and dissipation of energy that happens due to the filter? This is the question. Okay, so it's a combination of two effects, and therefore, with some applause, we have a podium on the third place. On the second. Very, very good. Very good. Very good. Okay, so thanks for this. Excellent. Yeah, so it was a pleasure for me. I hope it was also a pleasure for you. I need to put off my glasses because without them I can't see anything. So thank you, and then we will see tomorrow and the day after in the exercises. And with this, I will click on stop streaming and then we will distribute the prizes. Bye bye.